Third year. But I don't experience. No, I can't say so.
All right. So, welcome to lecture 2. Before we dive into the mathematics, a quick check. Any questions, queries, concerns about the course? Yes.
Just a question about one of the questions in the quiz.
Yes.
There was like a question where you gave us the seconds.
Yeah.
And we both had the same answer, but it's incorrect one. Like,
Oh yeah.
Okay.
The solution is incorrect.
Okay. So is this on the online quiz?
yeah.
Okay. Can one of you just send me an email with it and I will check it, just so that I have the. Yeah. Yeah. Okay.
I got an arithmetic mistake in a
Okay. Okay. So I just need one person to send me and I can check. And we can blame it on the textbook publishers, bad textbook publishers. All right. So I think, as you will have realized, like I am a human being. I make mistakes. Who would have thought? Like, I really, really hoped that when they gave me my PhD, I would like suddenly get everything right, but no, sadly not. Okay, so there is a chance if you are working on a problem and you get a different answer to the solution that you're correct. In which case, you should just say, "Hey Claire, this is my working. It gets a different answer to your working," and then I will check the two and I'll let you know. And if you did something wrong, then I will tell you. And if I did something wrong, I'll correct my solutions and tell the rest of the class. Seems very reasonable. Yeah? Yeah? Okay. All right. Other questions, queries? Okay, so it seems like we do have a midterm date finalized for in week 4 during the first tutorial period. So I think it's starting at 2. Yeah? Yeah. Okay. So if there are any problems, please let me know as soon as possible. Otherwise, that's what we'll do. All right. So what are we talking about today? We are finishing off a little bit from chapter 11. So remember, we were talking about curves and parameterization and stuff like that. We wanted to do a little bit of that. And then we are going into looking at a different kind of function. We're going to look at functions of several variables. So when we're talking about curves, we've been talking about a function of one variable where we put in a t and we get out an x, y, z. So we put in one thing and we get out this one thing. But next we're going to say, okay, if instead of putting in a single value like a t, what happens if we want to do something where we want to create a function where we tell the function what our position is and it spits out our velocity. This means we want to put in values for x, y, and z, and we want to get out something else. So we're looking at functions of several variables, and as usual, as you know by now when you're studying functions, the first thing that you want to do when you start learning about functions, you need to be able to talk about their rates of change. You want to be able to integrate them. So we need the calculus of differential calculus and integral calculus. We won't do all of that today, but in order to do calculus, we need to talk a little bit about limits and continuity. And we can pull quite a lot of what we've done before, kind of our intuition from single variable calculus, but we need to do like a little bit of work, like we've had to do every time we go up a dimension. We need to do a bit of work. So we'll talk about limits and continuity, and that will lead us to how we talk about differentiation when we're in functions of several variables. It's not quite as clear-cut as it is for functions of one variable. We have these things called partial derivatives, but they behave like we would want them to. And of course, once you can take one derivative, you always want to be able to take more. So we're going to be doing higher order derivatives. And your favorite that I know you're looking forward to, we're going to talk about the chain rule and how that looks. So this, I would say, is really going to build on your intuition from Calculus 1. And we're not going to go into the nitty-gritty details. I'm not going to make you do limit calculations. I'm not going to make you do continuity calculations. This is about building up your intuition, and then for these things, learning what changes when you're calculating these things, because there are some little differences. Okay, so that is our plan for today. So, just to remind you to reset to where we were last week, Monday, we were thinking about the situation where you want to describe the position of a particle as it changes over time. So you want to put in a time and you want to get out a particle. Or more generally, you just want to be able to describe a curve in three-dimensional space, which you can't do what we were doing when you were doing calculus in 2 dimensions, using x as your parameter and y as where your function was. Now instead we have a separate parameter, which we think of as time, but it doesn't have to be time. And for each period in time, for each value of time, we can say, okay, t of x is this, t of y is that, t of z is that, and that gives us a point in 3 space, and as time changes, our point in 3 space changes. Okay, all good. And as I say, it is important to bear in mind we're using t so that we have a kind of intuition for it, but t doesn't have to represent time. So you saw when you were parameterizing curves last week that you could use the angle to parameterize. You could pick some arbitrary thing that has no actual physical significance but just happens to be useful. You pick what works for you. So this is the picture that you have in your head. We have some parameter space here, and for each value of that parameter, we bring it into the space that we're interested in and find a point. In this case, 2 dimensions, but you could be 3. So this is just reminding you, we can use, one of the things that we use parameterization for is if we want to describe a curve in 3 space that we can't do simply by saying, I don't know, f of x, y equals whatever. We use parameterization. So this was an example where we used parameterization to describe the curve that is the intersection between a paraboloid and a plane. So that was last week. And as when you were dealing with ordinary, yeah.
I had a question about that. So do we just end with that last expression from the previous slide, or do we take the limit when time goes to infinity?
No, because remember what you want to do. So as the time changes, it maps out different points on the curve. So the curve is described by all time.
Okay.
So if I put in time t equals 0, then I get the point 0, 1, 1. And that's 1 point on the curve.
Okay.
I put in time t equals pi, I get a different, and so on.
Yeah. Cool.
So this is the other thing to remember with parameterization. You need to have your parameterized equation, but you also need to tell people what values you're parameterizing. So you would get a different curve if you only took, for example, t strictly bigger than 0. Then you only get half the curve, perhaps. So remember when you were parameterizing last week and you wanted parts of a circle or parts of an ellipse, you didn't take your angle to be the whole 2 pi, you took whichever bit you needed. So there are 2 bits to parameterization. It's the equations and it's the domain for the parameter. Yeah.
Cheers.
Yeah. Okay, so if you remember thinking back to Calculus 1, there were some provisos that you weren't going to work with weird functions that did crazy jagged stuff. And we apply the same thing here. We're going to have, avoiding really weird cases, we're going to assume, and it is a big assumption, that our parameterized curve has a continuous first derivative, where remember we just take the derivative by differentiating each thing. It's not too insane for a lot of the stuff that we deal with, but it's worthwhile keeping in your mind, just like you did with Calculus 1, we are making assumptions here. Okay. Notice that we're not saying that we have to be lovely and smooth. So we're saying that we need to have a continuous first derivative, but you might do something like that. That is kind of okay, and we can deal with this as a special case. But we don't want to have something crazy where we're doing weird-ass stuff like this all the time. So it's a bit of a hand-wavy thing. Okay. So that's important. We're dealing with nice curves. And the second thing is, and hopefully you saw this last week, parameterization is not unique. Okay, you pick the parameterization that works for you. So if you double check, all of these will describe the same circle, the same circle. Whichever parameterize you use. Firstly, in a test or exam, if I just say parameterize this thing, you do you. Okay, so long as it's correct, it's correct. But secondly, more functionally in everyday life, you would pick a parameterization that makes sense for your problem. Okay, so just a couple of vocabulary things. So we've got these curves in space. We talk about some special ideas. So if our start point and our end point are the same point, then we have a closed curve, so that's point 1. If it never happens that our curve twists through the same point, so we don't have two different t's for which the value is the same, other than our start and end point, then we say it's non-self-intersecting. And this makes life easy because, so here we have a non-self-intersecting. Here, if I hand you a t, you can tell me which, where I am, whereas, and you can undo it, and if I say, okay, I'm at this position, you can say what the time is. But the problem with intersecting curves is if I give you this position, you don't know which time it was. You're not sure if it was, I was coming along here, or if I'd already done that loop and come back here. Okay, so we're keeping it simple. Mostly we'll be working with non-self-intersecting. And finally, if we combine these two ideas of closed and non-self-intersecting, then we get a simple closed curve. Yeah.
If I could ask something. Is it necessary that like your starting and end points must, or the function and your start and end points must be equal for it to be closed?
Yes, to be closed, yes.
Because for instance, if you had like the function representing a circle from 0 to 3 pi, of course your start and end
Sure.
points are not
Okay,
the
so
same.
yeah, so then you have a closed curve. Well, technically you don't, because you would have, you can think about it in time, it's really doing this. It's not closed.
So if we add the dimension appropriate to our parameterization
Yeah.
variable,
Yeah.
it's no
Yeah.
longer closed.
Yeah, so this definition says it's actually about the parameterization, that the starting and ending parameter gives you a point that's the same point, then you're closed. Yeah, that was a good question. Okay, so time is something that we use to parameterize often, but it also turns out to be useful to have a kind of intrinsic parameterization from the curve itself, and this gives us the idea of arc length. Okay, so what are we going to do? Here I have a delightful curve. Okay, it's not closed, but it is non-self-intersecting. It's bounded, by which I mean it doesn't go tearing off to infinity in any direction. It's nice and contained. It's continuous, no breaks, no jumps. And we're just saying it's defined by some parameterization where t runs from A to B. Mostly we'll work with A starting as 0, but for the moment let's just keep it general. Okay, so this is the curve that we want to work with. And where we want to go, where we're headed with this, is we'd like to be able to measure the length of that curve in some useful way. So this is probably not something that you encountered in calculus of single variable, but you can imagine it's pretty useful if, for example, this is giving you the position of a particle. You would like to know how far it traveled. You want the length. Okay, so how do we do this? Well, we do what we do all the time in calculus. We start by breaking things up into small sections. So the first thing we do is we break it up into n subintervals. So we're dividing our parameter up into actually, so we're dividing the total length into n subintervals. That means that we need times from t0 to tn. So we have kind of n plus 1 times. Okay. All right, and we look at and what we do is we construct the straight line between each time interval. Okay, so our first time interval is r0, here is r1, and we do a straight line between those two. And that gives us an approximation for our red line here. It's always going to be shorter, but it's a start. And then we do that for each interval. So at a rough approximation, if we add up each of those arcs, if we add up each of those chords, where our chord length is just the change in position and use that to get our length, then this, summing those up, will give us an approximation for the length of the curve that we're interested in, right? Yeah? Okay, and as you know, since we've got a since we're dealing with a well-behaved curve, you can imagine as you make your time intervals smaller, so that your, for example, your next point might be over here, you're going to get a closer and a closer approximation. Okay, so this should all kind of intuitively be feeling quite familiar. So we're going to do something a little bit strange, but it's going to be useful. So I'm going to call my change in position, my Ri minus 1, delta Ri, just for ease. And we've got our index running over our n subintervals. And so I can rewrite my sum, my length of my little chords, as the sum. Everyone good with summation notation? Yeah, okay. So now it's not immediately clear why I'm doing this, but bear with me. Okay, I'm going to let my delta t, so my distance between my two time intervals, be delta ti. And what I'm going to do is I'm going to say Sn is equal to the thing I had before. And then I'm going to multiply by delta ti over delta ti. So I'm multiplying by 1. But yeah, it's not clear why, but you'll see in a moment. Okay, and it might be sort of becoming apparent, the way that I've written it, that this is going to become a derivative, and this is going to be a dt. And then we're going to be able to integrate. So that's the cunning thing that we've done. We're heading towards an integral, which we can do, which will give us the length that we're looking for. And do I want to do this? So the trick here, and there's a whole bunch of maths that I am sweeping under the rug here, is that as you let your delta t's go to 0, and your number, and hence your number of intervals going to infinity, there is a unique curve that you kind of end up with. And that curve is what we define as being the arc length. So we say S, which is our arc length, the thing that we're looking through, is this crazy limity thing here, which, if you think about what we had over here, so we're looking at this bunny over here, where when we let t go to 0, dt go to 0, as you know with calculus, we go from big deltas to derivatives, and we go from the summation to an integral. And that's incredibly hand-wavy. I realize this. If you would like more details, please come and see me. But otherwise, trust me, that what we end up with is that our arc length is the integral from our starting point to our end point of this bunny with respect to our parameter. Okay. What is this bunny over here? If we're thinking in terms of position, we know that dr by dt is our velocity. So the one thing that I haven't said is, why are there absolute value signs here? Well, there are absolute value signs because we know that we want our delta r over delta t to always be a length, a positive value. So we want to make sure when we come over here that we end up with something coming positive here, because we're always adding to our length. So that gives us our absolute value there. This dr by dt is our velocity, so we could equivalently say this. And over here, notice that I don't have my arrow on top here, so I'm talking about speed. And this, for me, is the useful one to get to, because you'll have this intuition from physics that if you want to find out how far you went, you just integrate your speed, not your velocity. So we're good. Yeah? Good enough? Okay. So we've done a whole lot of work to just get an equation that basically tells us what we already know, which is if you want to find out how far you went, you integrate your speed. Okay. But we're going to work with this arc length quite a lot. And so having this and understanding the derivation is going to be quite important. So part of what is going to be important about this is we could think of writing this as s is equal to some integral ds, where this is our arc length element. What do I mean by this? Really what we want to do is we've got our curve like so, and we just want to add up all these little bits, all these little ds's. We have done some magic to transform this into an integral in terms of a parameter, but ultimately this was what we set out to do. We wanted to just sum up all these little ds's. And having this notation is also useful sometimes to think about how to do it. So there's quite a lot going into arc length. I suggest you spend some time thinking on it. Will give you plenty of practice. So linking these two ideas together, our little ds that we're interested over here is the same as saying take a little time interval, and this is going to be equal to whatever your speed is times a little time interval. So this kind of links to your how you know velocity, distance and time all linked together. Shouldn't seem too weird. And so we end up, and we're just seeing this again, the length of our curve is either sum up your little ds, your little curve elements over the curve, or if you're parameterized, look at your velocity and add that all up from the start of your parameter to the end of your parameter. Two ways of doing the same thing. Quick pause. Questions?
Why do you have, so that for the integral of ds you started at e?
So that's actually a curly C. And this is, so that's a great question. So this thing over here, so this is a curve.
Mm-hmm.
And this says integrate
The whole curve.
over curve
Okay.
Z.
Cool.
Yep. And this says integrate over parameter t from t equals a to t equals b. And we will use both of these. All right, so let's do a quick check. Here we've got some position that's changing over time, and we want to find how far our little bug, whose position is given by that, travels from t equals -1 to 2. So let me grab a copy of this. All right, off you go. So I'm going to talk through this quite quickly. We won't get through to the final answer. So if we want to find the velocity, which is always a precursor to the speed, we take the derivative. Okay, so here I've got my velocity. Once I've got the velocity, how do I find my speed?
It's the modulus, the magnitude.
Yes, yeah,
Sorry, that's the question. Shouldn't it be the 2t times j and not
probably.
Yeah, not
Yep,
the d square.
yep. Good catch. Okay, so we're going to have, this is going to be 9t to the 4 plus 4t squared. I think.
Yeah.
Yep. Okay, and then we just integrate it from a to b. So in this case, from minus. So we're going to have the integral from -1 to 2 of this bunny. Okay. And you can solve this in whichever way makes you happy. Okay, so when you have a parameterized curve, then finding your length works like so. But let's just think a little bit about kind of a more practical situation. If we wanted to find the length, so we have a curve y equals f of x, and we want to find the length of the curve from x is equal to a to x is equal to b. Now what do we do?
I mean, one simple way would just be parameterize x equal to t, find out what your y ends up being,
Mhm.
and then just solve.
Yeah, so we could parameterize. So one possible thing would be to say, let x equal to t. So then, but how is that going to help us?
And if we know the function y equals f of x, and y is equal to, and now is equal to f of t.
Right, so we'd have y is equal to f of t, okay, and then?
Can we apply the same formula as before?
Yeah.
Okay, so you want to say,
Like now our f of t is in our r of t in a sense.
okay, so but be a little bit careful. You're in 2 dimensions, so really, what is your r of t here?
T and f of
is
t.
t
Yeah.
what t I plus f of tj.
Good.
Yeah.
Okay. Nice. So you can parameterize in a way, and then we would just do exactly what we just did before. And notice here we don't have a function for f, but if we did, so ultimately we'd be saying things like r dashed of t is equal to I plus f dashed of tj. So our v, sorry, this, which is our v, will be something like that. Integrate, away you go. Yeah. Okay. All right, so I'm just pausing for a moment here. So what have we added from last week? So we've taken the idea of parameterizing, and now we're saying, okay, I've got a parameterized curve, how do I measure its length? And essentially this is the way that we would go. So one thing that I think you should try and do is think for yourselves at home, if I wanted this little ds here, that tiny little length there, how could I approximate that? So how could I find, so if I wanted to instead write this integral like this as ds, what would this ds be equal to? And I'll give you a hint. You want to think about, what is happening here? Okay, I don't seem to be able to zoom in here. Do the usual thing that you do, which is you approximate things by using Pythagoras. So delta y, delta x, and think like that. See if you can get a kind of functional version of ds. And I'll put the solution in here.
Do we care about maintaining its direction, or do we just want its magnitude?
We just care about its magnitude. Okay. More questions? All right, so we are now putting on a different hat. So these are the kinds of things we've been looking at. We've been looking at a single point moving through time. So these are functions of vector function of one variable. But in a t, you get out an x, y, z. Okay. we move swiftly on to a new type of function where we're going to put in a point. So we're going to put in an x, y, z, put in something from R3, and we want to get out something from R3. And this is called functions of several variables because we're putting in several variables. Okay. It might feel a little weird because you know that a function has to take one input. You're like, but you're putting in 3 things. What are you doing? I'm only putting in one thing, but that one thing consists of 3 things because it's a point. Okay, so I'm not doing anything hinky. I'm also, and you know that functions are only supposed to send a single output for each input, and it might look, again, same thing, like I'm getting out 3 things, but those 3 things consist of one thing, a point. So I'm doing magic. It's great. So, a function, and this is where we have the actual definition, a function of n real variables, so I'm still staying in real land, is a rule that takes a unique real number from Rn, or from R3, well, from Rn, and assigns it to something in Rn. So it's just that I've changed my domains to consist of points in space. Nothing else really changes. We call the inputs the domain, we call the outputs the range. And as for functions of one variable, our convention says if I don't specify the domain, then it's going to be the maximum possible domain that you could have, the natural domain. Okay. So all the usual domain checking provisos are implied. Please don't divide by 0. If you've got a square root, because we want to stick in reals, please stay positive or 0. All the usual checking things apply. But if there's none of that, then just the biggest possible domain you've got. Okay, so we're used to functions of one variable are possibly painful but easy to graph. Okay, you know how to graph, and you have had to graph many functions of one variable. Okay, and you know that typically a function of one variable looks like a line. It looks like a curve. Okay. Functions of 2 variables. Okay, so how do we do that? Well, if I'm putting in, so here, this will not technically be a function of 2 variables. So this is a function, yes, so this is, I've got 2 variables that are going in, and I'm getting one value out. I'm getting a z, and I can plot a surface. Is that what I was thinking? Oh, no, okay, no, sorry. So here, my domain is something from x and y, so I'm putting in a point, and I'm spitting out a function in 3 space, so I'm spitting out an x, y, z. And I can do that, and I can get a graph that looks like that. I can get a nice surface. Okay, so long as I'm getting out something in 3 dimensions, I can kind of plot what I've got. But if I go beyond 3 dimensions, it's not clear exactly what would happen. Yeah.
So we say function of 2 variables when the input is 2 variables, and doesn't matter on the output.
Yeah.
So like we define, okay.
Yeah. Okay, it gets more complicated if I went to my definition over here. If I'm starting to look at 4 dimensions, who knows what these bunnies look like? Okay, we can have some tricks to kind of help us look at them, but we can't actually plot them. So I won't be asking that in a test or an exam. And I pretty much won't ask you to do plotting in 3 dimensions in a test or exam. I might ask you to think about them in tutorials and kind of try and do sketches, but it's tricky. Okay. So if we want to think about plotting things that live in higher dimensions, one of the ways to go about it is thinking about level curves, and they're also going to help us analyzing these functions. So a level curve is exactly what you might think. So let's start it where we're thinking about a function of 2 variables. Okay, so we've got something that looks like this. And as you know, if you studied geography or anything like that at school, one way to visualize a surface in 3 dimensions is to say, okay, let's just keep the height constant and see what the function is doing at that point. And that's exactly what we're doing with level curves. So we pick different values we let our function be constant, and then we solve for that shape. So for example, in our surface over here, if we say, okay, I'm thinking about when z is equal to 45, when z is equal to 45, what does my function look like? Well, it looks like just a circle there. And if you do this, so you might not know what this function looks like, but if you pick a whole bunch of different z values and you plotted all of these, then you could say, all right, I can see that when my z value is lower, it's kind of a big circle. As my z gets higher, it gets smaller and smaller circles, and so you build up this picture here.
So z is k.
So z is a variable, and we pick particular values of it, which we call k. So k's are our constants,
Okay.
which we use. So basically we pick a k, and we substitute it. So here we would have an equation, for example, f of xy is equal to x squared plus y squared, say.
Mm-hmm.
And then we say, all right, well, let's pick a value of k, for example, 0. When k is equal to 0, what is 0 equal to f of x squared plus y squared?
Mm.
It means we are solving the equation 0 is equal to x squared plus y squared, which is a point. And then we pick another value for k, so we pick, say, 1, and we plot the graph x squared plus y squared equals 1. It's a circle, and so on. Make sense?
Okay.
Okay. You have been spotting functions of two variables in the wild for a long time. Every time you see a contour map, that's a function. These are level curves, and you know how to read them. Okay, so if we have a look, we've got a lonesome mountain here. The highest point, well, we can see here's a contour at 5,000, here's one at 5,500. So we're moving up here, and there's a good bet that this little point up here is the highest point. And we can get an idea of the shape. Things like that. And in fact, heat maps, things like this, these are all giving us all things using level curves. So here, this is a slightly different kind of level curve. So this is giving the average air temperature near sea level. So you can see that right in the center, at the top of Africa, in July is probably going to be our hottest place. And you can use coloring to help see your level curves as well. Okay. So why am I pointing this out? I'm pointing this out because we have a lot of new concepts in this course, but actually you should have a fair amount of intuition for this. You know what a level curve is. You've seen them a lot. Attach that intuition that you have to what we're doing, and it will help. Okay, so, all right, so that was functions of two variables, and they have level curves, so they have a single curve. Now we're going up one dimension. If you have a function of three variables, okay, so you're putting in three variables, you're getting out three variables. So those, the actual functions represent solids. So if you want to think about what are the level curves of a solid, they're actually surfaces. So if you think you've got a nice big sphere, well, its individual kind of curves that you would think of are the individual empty spheres within it. Yeah? Okay? And you use exactly the same trick, and this can help you visualize. So to find a level surface, so here we have a function, I'm putting in an x, y, and a z, and I'm getting out a function, I'm getting out a value over here, a single value. So what I'm going to do is I set this to be a constant, and then I look at this thing, and this thing over here is a surface. So I just want to go back. I think I misspoke at the start of this. I can't remember, but if I said incorrectly, what I should have said at the very start was we're putting in a point, so we're putting in an x, y, and a z, and we're getting out a single number. Did I say that? I can't remember if I did. Okay, all right.
You said a point.
Okay, so I should have said we're getting out a single number. Okay, so that will probably help clarify why when we look at this picture over here, we're putting in an x and a y, and we get out one value, which is our z value. Better? Yeah, I'm sorry. And also, it will clarify why, when I said a function of 3 variables, what we're putting in is a point in 3 space. And now I need to plot it somewhere else, in a 4th place. I don't know where to plot it. Better?
Mhm.
Yeah, okay, sorry about that.
So is it like the opposite of our RT?
Yes, in fact. So previously we were putting in a t and getting out an xyz.
Okay.
Now we're putting in an xyz and we're getting out a t, but it's not a t. Okay. Yep. Okay.
Yeah, and
And very soon we'll be doing what I'm sure you're all waiting for. We'll be putting in an xyz and then we'll be getting out an xyz, but we're not there yet. Okay. So now we're putting in an xyz or an xy and we're getting out another value. If you're putting in an xy and you get out another value, you can plot it in 3 dimensions because you've got your 2 dimensions for what's going in and your 3rd dimension for what's coming out. But if you are putting in an xyz, that takes up all the dimensions we can draw, and the thing we're getting out is in a 4th dimension. Okay, good luck with that. And hence why we draw level surfaces, functions of 3 variables. So to find a level surface, we set our function equal to a constant, and the level surfaces are, and this is, okay. We're not going to do too much about this, but it is useful to think, to have a kind of an idea of how you would go about visualizing a function of 3 variables.
So in this particular case, level surfaces would be indeed spherical surfaces, right?
Mhm.
With weight scale.
Okay, so we can see this. So for example, let's let k is equal to 0. We get 0 is equal to x squared plus y squared plus z squared. So that's just a point at the origin. And then if we took k is equal to 1, 1 is equal to x squared plus y squared plus z squared. That is a sphere. And then we keep getting more spheres going on. Okay, so that was just a hasty introduction to functions of several variables, 2 or 3. And the next thing we need to do is how do we talk about their rates of change? Because suppose I tell you that you have some function that is changing with time, and it's a function of 2 variables. You want to be able to quantify how that is going to change over time. Is it very quick? And what does it mean to be very quick? Things like that. And this leads us to talking about derivatives. And in order to talk about derivatives, we need continuity. In order to talk about continuity, we need limits. This is going to be quite hasty. So take your mind back to calculus 1, because we're going to use that intuition. Okay, informal definition of a limit is, so what do you have in your mind if I ask you about the limit of a function? What?
It's the value at which the function is approaching as much x goes closer to something.
Right. So it's the value that you think the function should go to based on its behavior either side of the point that you're interested in. So you have some function that's doing this, and if we're interested in this point over here, what do? Well, you look at the function's behavior over here, you look at the function over there, and you say, ignoring what it actually does at that point, the limit is that point because it should be going there based on that and that. Okay. And you can do the whole epsilon delta thing if you want to be precise.
Just never got it after I think
Sorry?
I've never get the formal definition of limit, how it works. After calculus, I suppose, still don't understand that.
I would love to spend time
Yeah, I
describing it.
know.
I mean, I still have to. So I can do this. You'll be glad to know. But I still, when I'm thinking about it, I use that thought in my mind, and then I translate it into this. So one thing that might help is for you to go through this definition with that picture in your mind and think about what it's saying. If you're bored one day, and you've done all of your calculus, your multivariable calculus homework. Okay. So how do we, so now we're talking about surfaces, for example, if you've got a function of two variables. How do we do this? Well, the picture you want to kind of have in your head is, here is my surface, and I'm interested in the limit at a particular point here. How would I decide that? Well, I can't just decide by looking at what the function does, for example, there and there, because it does stuff here as well. So instead of just looking kind of for a little bit on either side in one direction, I look at neighborhoods around here. So what I do is I say, okay, based on what my function is doing, maybe this will help, in this neighborhood around there, not counting the actual point, but based on what it's doing around here, what should the function do at that point? And that would be my limit. So it's the same idea, but it's just using a neighborhood instead of little areas on either side. Okay, and that's as much as I'm going to say. But you end up with an epsilon delta definition that looks kind of similar. And you can link the two together if you feel interested, the single variable and two variable versions. Okay, so why did we do that? I did that so that I could tell you that we do have a way of talking about limits of functions of many variables. And if you go to 3 dimensions, so that was just the two functions of two variables, 3, then you extend the idea, and instead of talking about a little neighborhood, you'll talk about like a little ball around the point. And then it just gets hinky after that, but the same logic will work. So we can, once we've got limits, we can talk about continuity. So what is your idea of continuity in function of one variable? And how does it link to limits?
When the function is equal, if the left limit and right limit are equal,
And the function
and
and
the function is
the function. So basically continuity says not only the function does what you think it should do. So the limit tells you what you think it should do, and continuity will tell you that it does what you think it should do. So you have a situation where so here's my function. I'm interested in this point over here. My limit says, okay, look over here, look over here. I think that the limit should be that red dot over there. And then you look at your function, and it is, the function value is the red dot. Yay, we're continuous. Useful to have the alternative in mind, which would be okay, so here's almost the same function. But now, if you look over here, and you look over here, the limit should be this point over there. Based on the behavior on either side, that's where the limit should be. But my function value is over here. They don't coincide, so by this definition, the function is not continuous. And this is exactly what you want to happen. You want to say a function is not continuous when it's got a break like that. Okay. And we can play exactly the same game for functions of two variables. We can say, well, I'll find the limit of my function, so using my little neighborhood, and if my function value equals the limit, I'm continuous. Yay. Okay. So the intuition applies. Okay, so we've dealt with limits, we've dealt with continuity, which means, yay, we can do differentiation. Hurrah! How do we do this? Well, again, think back to calculus 1. What was differentiation? It was about finding the tangent, the slope of a tangent to the graph. Okay, and you've done that a lot, and you know how to do it, and that was all delightful. So, functions of two variables, what can we do? So, if you think about it, functions of two variables, we have a little bit of a problem. So I've got a nice paraboloid here, and I'm interested in the tangent at a point. But if you think about it, I've got infinitely many tangent lines at a particular point, and they all point in different directions, which is really freaking annoying. So we don't have a simple, straightforward, like, bam, there's the derivative, let's move on with our lives. We need to do a little bit more here. So, essentially what we do is we say, okay, I don't know how to do derivatives in 3 dimensions, okay? But we know very well how to do differential derivatives in 2 dimensions. So let's simplify our problem. And the first thing that we're going to do is we're interested in finding something like a derivative at a particular point. We're going to hold the y value constant and cut our surface with y constant. So what I end up with is really just a curve in the x and z plane. And curves we're great with. And then we find the tangent at that point. But we have done something there. We've held y constant. So we can't just say that's the derivative. We need some way of saying I was holding y constant. So we have what ends up being called the partial derivative of x with respect to x. And as soon as I say it's with respect to x, I know that I'm holding everybody else constant. So in this case, I'm holding y constant. But that doesn't give us all the information. So the next thing we do is we play the same game, but instead we hold x constant. So we have essentially sliced our surface with plane x as some constant, and then we find the slope in the y direction, and that gives us the partial derivative with respect to y. And it turns out that if we know the partial derivative with respect to x and the partial derivative with y, we pretty much can categorize the slope for whatever value of slope we're talking about here at that point for a function of 2 variables. And thinking further forward, if you had a function of 3 variables, then you would get partial with respect to x, y, and z, and those 3 partial derivatives would characterize your slope. All right, so let's look into that in a little bit more detail. So let's look at an example. So here's my function. Did I put this here? So here's my function minus x squared minus y squared minus 4, and we want to find the partial with respect to x, so holding y constant, and the partial with respect to y, which is holding x constant. So this is where you need to have a warning sign that goes off in your head. Whenever you see these things, this means partial derivative, and it says hold y constant. And the reason I say you need to have a warning is because holding y constant means y doesn't change. So y behaves exactly like a constant. So you differentiate it like a constant, not like a variable. How do you differentiate a constant?
It goes to 0.
It goes to 0. Okay. And this is where you have to undo several years of muscle memory of differentiating variables like variables. And I promise you, you will screw up at least once, and then you will kick yourself. Okay. So kind of just make a mental note for yourselves. As soon as you see these funny squiggly Ds, be hyper careful. Okay, so we want to find
Sorry, can I ask you something?
yes.
Why are we not keeping also z constant? Like, why do you choose y and x?
So here, z is where's my function? So this is really z is equal to minus x squared minus, sorry, it should be a y squared plus 4. Z is our dependent variable.
Okay.
So just like if you've got y is equal to 6x plus 4 and you want to find the derivative,
Okay. Yeah.
you wouldn't take the derivative of y.
Thank you.
Okay, so let's go ahead and find these. So df by dx. So I look at my function and I say, okay, my y is being held constant here because I'm only looking in changes in the x direction. So what do I get?
It's minus 2x.
And that's all. Okay. All right. And if I find df by dy, I hold x constant, so I'm going to get a minus 2y. All good? Okay.
Okay, just a question. Because sometimes I saw annotation and when it was doing like other courses where, for example, for the partial mathematics, I'm confused if I have f and then a small x as a padding.
I'm getting there.
Okay.
Yes, I'm about to talk about the horror that is the notation.
Because
Yes,
I
Yeah.
always forget which variable I have to differentiate between.
I know. So my recommendation, if you want to have a long and happy life, is use this because that keeps it clear exactly who you're differentiating, whatever. Okay, but I will show you the rest of the differentiation. Okay, I will leave this for you to do. Just remember things stay constant, okay? But use the product rule, and you can check that at home. So, here is the notation. So you could write what we've been doing, which is df by dx. But in the same way that you used to call f of x y sometimes, here you can call f of x y z, so you might have partial dz by dx. And then, and this is very annoying, sometimes if you magically know which is your first variable, you'll put f subscript 1, which says take the derivative with respect to the first variable, which in this case is x. Okay? Or sometimes you use a big D, because that means take the partial with respect to the first variable. And then there's also the notation that you've seen, which is f with respect to x of xy. It says take the partial with respect to x. Or you could also sometimes see big D x. Okay. It's annoying. And we use the same notation that we've used for finding, so this is finding the general derivative, so the function that is the derivative. If you want to find the value at a particular point, we use the same notation that you've probably used before, so the line and the point that you're interested in, or this notation line there, or this where you've just plugged in the particular point with the subscript x or as you would. Okay. So there shouldn't be anything particularly weird and new there. Okay. So we've already basically got this. I don't know. So now I've got my same function that we just had, and I want to find the value of the partial derivative with respect to x at the point xy equals 1. Well, we know that df by dx is equal to, I think it was minus 2x. So okay. All right. So now I have a little challenge for you. Let's find a vector which is parallel to this line here, to our tangent line, because it's actually going to be very useful where we're headed with this, we want to find equations for tangent lines. And we know that in 3D, in order to find the equation of a line, we need a point on the line, and we need we need a point on the line, and we need a vector in the direction we're interested in. So our first step to finding tangent lines is finding vectors in the direction that we're interested in. Okay, so my question for you is, I've got my plane where I've held y constant, y is equal to 1, and I've got my intersection parabola over here, and I want to find a vector that lies on this line here. Go for it. Okay, we've already calculated a bunch of stuff. Okay, we've calculated the rate of change of f in the x direction. So okay, so I'm just stepping away from this because I want to find an image that I hope will help. You are using 1, 1.
Why are we using 1, 1?
Because I liked it.
Okay.
Oh yeah, just y to be 1, then
Okay, so I can't find my GeoGebra applet, so we'll have to do this in our heads, which is a little trickier. Okay, so we're keeping things constant in the y direction. So let's think about what would happen if we looked at this. So positive x is coming out here, positive z is going up there. So if I wanted a picture of that curve that I'm kind of used to, if I look from the back, what I would see is I would see this, where I've got x there and z there. And what I'm interested in is, and I'm interested when x is equal to 1, which is about here, and I want this tangent line there. So the first thing to notice is that if I just asked you to find this tangent line here, and you'd found a tangent line of you'd found a slope of -2, you'd be very happy with that, because it's going down and that looks right. And we have that information over there. So one thing to do when you're getting used to this is to plot things like this and check that the slopes that you get go in the right direction. And similarly, if we had plotted, if we'd looked at in the y direction, we got another -2. Think about where we're looking at it. We're looking at it from the back here, and you'd be looking here, and you would again have, you'd be looking from the front. You look at the front from this direction over here, and again you'd have a slope of -2. So it makes sense. Okay, so we're wanting this blue line, we want that vector. Well, can you describe to me in vector form what that -2 tells us. So we want a vector that basically does something like that.
For each one step in the x direction, we take -2 in the z direction.
Perfect. And what do we do with our y component?
0, since they don't move in the y direction.
Right, so we can construct a vector which says, okay, if I want this vector here, what must it do? Well, so what am I going to call this? I'm going to call this our tangent vector. Well, if I make a step of 1 in the x direction, it needs to go -2 in the k direction and nothing in the j direction. Does that make sense? Okay, so we're using our information that says, okay, I know what the slope is there, and my slope tells me that if I go 1 step in my independent variable, then I will go slope steps in the dependent variable. So your intuition is there, we're just pulling it into vectors. And so now you should be able to tell me if I wanted instead a vector in the y direction of change, what would that look like?
0, 1, -2.
Right, it would look like, so this is my, I'm going to call it my tangent in the x direction, my tangent in the y direction. I don't change my x, so I've got a 0 in the I, I've got a 1 in the j, and I've got a -2 in the k. Based on this is df by dy evaluated at 1, 1. Okay, so it happens in this case that the two are the same, that our two df's are the same. This won't always be the case. Alright, so this is very important. This being able to find a vector in the direction of change holding one variable constant is an important thing to be able to do. Because it's going to lead us to what we ultimately think of as our kind of proper derivative, which is thinking about tangent planes. Okay, so I'm pausing there for a moment. Any questions?
Can you re-explain the last step for the vector solving?
From where?
I get the derivatives, I get the line, I get the derivatives, tell me the...
Okay, so you're good? This is good?
Yeah, this is good.
This is good? Okay, so what we want to do, so we found the derivative, which is the slope of this blue line there. So the slope of that line is df by dx, which is equal to -2. Is that good?
Yeah.
Okay, and that picture is we've drawn here.
Okay.
Okay. What I would like, but the -2 is not super helpful if I'm in 3 dimensions. If I say the slope of the line is -2, it's like, I don't know. We need vectors to talk about our slope properly. The only reason that we know that this is the slope is because we're holding y constant here. So what I want is a vector which points, I want to find a vector that points along that line. Okay. Well, what do I know about that vector? Essentially, it's this vector here. I know that it's a vector that it doesn't have a y component because I'm holding y constant. Okay, so there's a y component there. And in order to be that vector, this vector has to have the same slope as this. So this says if I put in x is equal to 1, then my z must be -2.
Okay.
So I could have, there are an infinite number of vectors I could have picked. I picked the easy one, which is change x by 1, then z must change by -2. So change x by 1 and your z changes by -2. Yep, yep.
Why do we look at the picture from the front or the back? Like, how do we understand the picture?
Okay, so good question. So the way this is drawn, positive x is here and positive z is there. So we're used to drawing things with our positive x going to the right and our positive z going there. So if I look at this, I see, well, positive z is going this way. If I looked at it from here, positive x would be going that way, which I'm not comfortable with. So instead I look from the back. But if I look at y, positive y is coming out the board, and that's kind of almost the right direction, so I'm looking from this side. Yeah. Okay. So what have we taken out of all of this? We have taken out that if I give you a surface, and I give you a point on that surface, you can find two vectors that are tangent to that surface, one in the x direction and one in the y direction. Not necessarily. So they're not in the x direction and the y direction. They're sorry, I should have said we can find two tangent vectors, one where you're holding y constant, so it just changes, it's in the xz plane, and one where you hold x constant, so the vector lives in the yz plane. That's better. Yeah. Okay. Where do we go with this? So we're headed, we would like to have a unique thing that tells us about the rate of change of the function. So far we've not achieved that, we've achieved two things. And you can imagine that, honestly, we just picked the x and y directions, but you could pick a plane going through at some other crazy angle, and then you could find a slope there. So you could find partial derivatives in whichever directions you choose. So there's nothing unique there. We don't have our single unique thing that's going to really tell us useful information in one thing about the change of our function. However, if we have a well-behaved surface, the thing that is unique at a point is the tangent plane. So, and this is kind of the step in functions of one variable, so calculus 1 that you did. There is given a well-behaved function, you have a unique tangent line. If you step into the world of surfaces, you don't have unique tangent lines. We've seen there are an infinite number of them, but what you do have is you have a unique tangent plane. You've gone up a dimension, you've gone from lines to planes. So the thing that we want to find is the equation for our tangent plane. So let me try and get this picture here. Let's do it. What happened there? Okay, so to give you a picture of what we've done so far, here's our function, and the two vectors that we've found are this one here and this one over here. And if I put them together, I feel like I should have my tangent plane here. Yes, there it is. Okay, and for a moment, I'm just going to hide that vector. Okay, so what we've found is we found those two vectors, and they lie on the tangent plane, which is this blue thing over here. And you can see we would have any number of vectors lying on that plane, but the plane itself is unique. So that's the thing that we want to find. Okay. And now we use what we learned last week. What do you need in order to find the equation of a plane? You need a normal and a point. Okay? We've got the point because we've just been working with that. Now we need the normal. Okay? What do you know about the normal to a plane?
It's normal for vector, so we can just make the cross product of the two vectors we calculated.
Perfect. And that is our plan. Okay. So the whole procedure that we've done is we have found two vectors that lie on the tangent plane by doing our partial derivatives with respect to x and y. And now we're going to take the cross product, which will give us a vector that is perpendicular to the plane, and use the point that we have on the plane, and then we have the tangent plane.
So is that why we had 3 vectors in the previous thing that you showed? Because one was the cross product?
Yes.
I kind of missed. Okay.
Yes. So now I can go back to that and I can show you. No, stop doing this. Sorry. Okay, here we go. All right. And if we take the cross product, we get that vector, haha, which is perpendicular to our plane. Okay. And the direction of the normal. So there's 2 things that are unique here. Our tangent plane is unique, or equivalently we could say the normal direction is unique. Not the normal vector, because you can have different lengths and it could be pointing this way or that way, but the direction is unique. Yay! Okay. So this is why we did everything we did last week around finding lines and finding planes and cross product. We need it because this forms the basis of our calculus of functions in 2 variables. Okay, so you can read this. It is exactly what we just did with a lot of words, which I find unhelpful. Okay, I look at paragraphs like that and I'm like, I can't. Okay, what I can do is think through the reasoning that we did over here to find this vector here, and that's exactly what that paragraph says. Okay, so you find your tangent vector in the x direction, find your tangent vector in the y. I'm going to just put over here that in fact the general equation for your t of x is going to be I plus df by dx evaluated at the point you're interested in the k direction, and similarly okay. If working with lots of words works for you, by all means read that paragraph. And I've called mine tx and ty just because it helps me. But out of that, we've got our 2 vectors that are lying on the plane. We cross product them, and we end up with this thing over here, which might perhaps look more helpful if you write it as this is df by dx evaluated at point AB in the I direction plus df by dy and memorizing this, it's really important if you're memorizing, but you don't need to because you'll have a formula sheet to have that minus k. All right. And this is not unique. So here we chose to go T2 cross T1 because then the formula looks like that, but there's no reason why you couldn't have said T1 cross T2. You'll get a different normal, but it's pointing in the direction you care about. It's a normal, it's fine. So I do not expect you to, if you do this from first principles, because it's quicker for you than kind of memorizing stuff, just get a normal. Okay, just find a normal. Okay, so note here it's saying a normal to that surface at the point AB is this bunny here. Okay. So that was actually just going to be my rough explanation, but I think I've basically done it here. So what follows is the details. And as a summary of what we did, what we do is we first find a vector by holding y constant. We find a vector by holding x constant. So we get our 2 vectors over there. Then we cross producted to get our normal vector. And then finally we could find our equation of a plane by using the dot product. And I'll fill these in, but I've already actually said this. So this is I hat plus okay, do the same thing over here, and there's our normal vector. Okay, so I've done this like a bunch of times in here because I know that there are a lot of steps. So if you read through these notes, I would recommend that you read through it the 2 times that I just did it, so that your brain gets through all the steps to go. Okay. All right. So let's find one. So we've got this surface. A normal vector at this point is, well, we've already done most of the working here. We know that our Tx is I hat minus 2k hat. Ty is j hat minus 2k hat. So let's find a normal vector. Okay, pick your favorite. Pick your favorite method of finding your cross product, whatever works for you. 0, that's going to be 2i hat. I think.
It's minus 2i hat.
I don't think so.
No.
Oh.
No.
Oh yeah, no, sorry.
Yep.
Sorry.
Okay.
Hmm?
Okay, I'm not even going to talk you through my method because you might have different methods.
I think the order you did it makes everything negative, because we would normally get minus 2, minus 1.
Okay.
I mean, it doesn't matter because it's all
Yeah, it doesn't
scalar
matter.
multiples.
Okay, so in the formula that I just gave you, I think they did ty cross tx, and then you'd get negatives. But yeah, whatever. So the reason I think that they did it is if you do ty cross tx, then you get minus 2i minus 2j minus k, and the point here is that these minus 2's are your partial derivatives. So you can just kind of plug in, but I'm not a fan of just plugging in. I do things from first principles, but you do you. Okay, so there we go, normal vector. In fact, for the price of 1, we got 2, because here are the different ones. Okay, they're just pointing in opposite directions, but they're good. Phew. Okay, yeah?
So no matter which formula was given there, you were just counting the determinant, or we take into account the minus, which was in the formula.
So here we just, I mean, the formula just used a particular cross product, which happened to give you a minus. I didn't use the formula, I used the fact that I just want a normal, so I just take any cross product will do. So the key thing here is not the direction. I mean, the key thing here is not whether you've got a plus or a minus here. Either one is a normal. So I suppose what I want to say is, if you're happy learning formulae, learn this formula. And remember there's a minus sign. I cannot remember formulae and they make me twitch. I prefer to do things just thinking through the logic myself, which is what I did here. And this one is perfectly valid. It's a norm. Okay. Okay, sure. Okay, so remember where we're headed. We're headed to finding this wretched tangent plane, which we know is unique and is going to be super important. We're almost there. We found the normal. We have the point. All we have to do is plug it into the equation for a plane. How do we find a plane in 3 dimensions? Okay.
The last one, so I take the
Right.
normal and then I do dot product
Right.
with r, which is a variable, and there's 0, which is my points.
Right. So we use the formula that we learned last week. Now we have our normal. We know some point because we've just been working with it. And off we go. And we found our equation to the plane. If you plug that in and you use the normal that they did up there, then you will get an equation that looks like this. But remember, there are many equations for planes. So you might, depending on which formula you do it. So you could have different normals here. You could have, well, your point is always going to be the same, but different normals. But notice, the only thing that changes with a normal is the signs. And since you've got an equals over here, you can divide through by -1, and you'll end up with the same equation. So whichever normal you use, it doesn't matter. Yeah. Okay. Ha! Great. We have tangent planes. Phew. And it's not even past yet. Okay. So plugging in exactly what we just did, we can get the equation for our tangent plane at that point, which was what we wanted. Okay. So I realize that this is slightly more involved than finding the equation of a tangent line. Sorry about that. But it's also more fun, really. It's kind of like, there's a lot more interesting stuff going on here. So, yeah. Okay. So, before I head on to this, any questions? Okay. Please, please, please spend some time finding vectors that are tangent to curves at points, so using your partial derivatives, and then finding tangent planes. Like, I cannot stress. So, Sane at the back, you remember all the tangent planes you had to find. Okay. She's sitting in again. She passed the course, but she loved it so much that she's back. Or something. Okay. So, tell them, find tangent planes. Yeah. Yeah. I mean, basically, finding tangent planes is as important as finding tangent lines, only more so, because now you're in many dimensions. Okay, I'll stop now. Okay, so joy and delight. It's not enough that you get to take one derivative, or one partial derivative. Now you get to take higher order derivatives. But guess what? You have multiple dimensions. So if, for example, you have dz by dx, this, remember, is a function in its own right that lives, it's a function of x and y. So you have two choices of the second derivative that you could take. You can either take the derivative with respect to x again, so you get a dx squared, or you could take the derivative with respect to, where did it go? Or you could take the derivative with respect to y. Okay, so if you have a function of two variables and you're taking higher order derivatives, you don't have two higher order derivatives, you have four, because you can take dx partial with respect to x and then again with respect to x, but you can also take partial with respect to x and then with respect to y, and the same with y. And if you go into 3 dimensions, then you have 9 higher order, and so on. Okay. So keeping in line with like using sensible notation, I would highly recommend that you just keep just writing these partials out. Because one of the things that I always find tricky, so it's very clear here which partials you should be taking, because you're taking it twice. But the question is, here, who do you take first? Now it turns out actually it generally doesn't matter. It's going to turn out that the partial with respect to y and then with respect to x is the same as the partial with respect to x first, then with respect to y. But I prefer this notation which says take the partial with respect to x first and then with respect to y. If you're needing to think about this and you're wondering, looking at this, who should I take first, you take whoever is closest to the f first. So you take the derivative with respect to x first and then with respect to y. You move outwards this way. In the same way you would have your f over here, I mean, when you've got your z there, you take with respect to x first because it's closest to z, and then you take the next one. Right? Okay. All right. So you can go ahead and do this. Not a lot to say. I think this is the key point over here. When you have mixed partial derivatives, so first with respect to x and then with respect to y, as I've just said, actually it doesn't make a difference. You can check that yourself you should have noticed that when you go through these examples.
Sorry, I didn't quite get why would we now then do this?
Okay, so the question is, why would we do this? Why is she making us take more derivatives? Because in the same way that in calculus of 1, you want to talk about velocity and you want acceleration, second derivative.
Oh, I see. Mm-hmm.
So we're interested in second order changes.
Okay.
Yeah. Yeah. Okay, and I will, I think you can just read through the stuff on the chain rule. I'm not going to go into a lot of detail. The point about the chain rule is that it depends on what your function looks like. So read through this. We'll do a quick recap at the end of next week, at the start of next week. Otherwise, go forth. Find tangent planes, please. Find them. Okay. All right. Enjoy your week.
See you later.